Hello dear children, in today's class we will be discussing the equations of motion by using a calculus. We are going to derive the equations of motion. Dear children, this is the fourth lecture on kinematics. In the first three lectures we covered distance, displacement, velocity, speed, acceleration, retardation. So links will be given in the description. Just go through those videos to get a complete concept from the beginning. Yes, so when it comes to the today's session, children, purely we will be using the calculus method. So means these equations of motion even can be derived. General method we have, graphical method which we have, and a calculus. So when it comes to the calculus method, children, this is very important, and here differentiation and integration is involved. Children, here how many equations of motion do we have? Here three we have. V is equal to u plus at, S is equal to ut plus half at square, and v square minus u square is equal to 2as. And of course the fourth one also which we have, that is especially which we use to calculate the distance traveled by an object in a nth time. So there's a special one actually. So we discuss after learning these three equations of motion. Clear? Fine. So children, here one important point actually. Of course, before going to start our equations of motion, children, before going to start deriving, so we should have a minimum knowledge about the actually we should know about clearly a differentiation integration, but at least a few formulas are needed to understand the equations of motion. So first let us see that, then we can go to the derivation part of equations of motion. Clear? Fine. So children, here integration of dx, this is very important. So integration of dx can be x. Okay, as I told you, we are not going in depth, just I want to recall. Okay, so similarly integration of dv can be written as v, integration of dy can be written as y. So when it comes to the here, children, so here in integration actually we have two types of integration. Okay na? So indefinite integration, definite integration. What is the difference, children? In an indefinite integration, children, just we don't get we don't have a limits. In a definite integration, yes, we will have a limit. So from here to here, something like that. Okay, so this is actually indefinite integration. So of course you forget about the types of integration, all these things. So let us focus on the formula which we are going to use. Okay, so integration of x power into dx can be written as x power n plus 1 by n plus 1, which means what? Whatever the power is there, further just add 1 by power plus 1. Example, it is given x integration of x dx. Children, here x power 1 will be there if nothing is there means. Okay, so x dx means what? X power 1 plus 1 by 1 plus 1. So obviously it is a x square by 3. Next it is integration of y square can be written as y power 2 plus 1 by 2 plus 1. So it is y power 3 by 3. Okay, fine. So when it comes to this is actually definite integration where limits are involved here. So integration of x dy, so same manner, same formula we are using, that is x square by 2, but we need to apply the limits. So this is called lower limit, it is called upper limit. So after doing integration, so we have to substitute the two given limits. So here first you have to substitute the upper limit minus lower limit. So based on that it is written as x2 square minus x1 square by 2. So children, so these are the formulas which are very important in order to derive the equations of motion. Okay, fine. So when it comes to the equations of motion, so when it comes to the equation of motion, children, here we need to specify, we need to highlight about our physical quantity. Of course, here many physical quantities are involved. What are those? Velocity, their initial velocity, final velocity, displacement covered, time, acceleration. Yes. So children, what is mean by acceleration? So it is a rate of change of velocity, that's fine. But here in acceleration, again we learned, right, uniform acceleration, non-uniform acceleration. So what is mean by a uniform acceleration, children? As it is the change in velocity by time. So how that change is going to take place is very important. If there is a the change in velocity is happening in a uniform manner, then we can say that it is a uniform acceleration. If not, it is a non-uniform acceleration. Let us recall once again what is meant by uniform acceleration. Children, look at here. At a point A, let us say that the body velocity is 0 meter per second. After 1 second, let us say that 2 meter per second. So after one more second it is 4 meter per second. After one more second it is 6 meter per second. So let us see that, children. Means in each and every second, if you can see from here to here, that velocity is increased by 2 meter per second only. Here it also 2 meter per second. Here 2 meter per second. Means the change in velocity is a uniform. Means if you want an acceleration, children, here, so you can take any, you can take any time interval. Any time interval you can take. You will get a 2 meter per second per second. So you will get a 2 meter per second square. So this is what very important. So now why we recalled uniform acceleration? Because, children, these equations of motion are applicable only for an objects which are moving with a uniform acceleration. In fact, we assume a situation where objects are moving with a uniform acceleration and we derive. That's what, as we are deriving equations of motion for an object which is moving with a uniform acceleration, obviously these are applicable only for the situation where bodies are moving with the uniform acceleration. Children, this is a very important. You may get a one doubt. Sir, then how to calculate an acceleration if an object is moving with a non-uniform acceleration? Yes, for that we have a differentiation method and integration method. Children, if acceleration is uniform, yes, we will involve equations of motion. If acceleration is non-uniform, we have to go for differentiation concept and integration concept. Is that clear? So this is the condition. Equations of motion are applicable only for an objects which are moving with uniform acceleration. Clear? Yes, children. Now let us derive the first equation of motion. Yes. So now let us see the situation, children. So let us consider an object. Okay. So when the time is 0, you may get a note, sir, how a time can be 0? Children, time won't be 0. Time can't be 0. Okay. But the moment when we start observing situation, that moment we consider as a time 0. It doesn't mean that time complete 0. So the moment when we start, so that time we assume it as a time 0, then we start counting. Okay, fine. And here one more important thing is that here, the moment when we start observing the motion of an object, observing an object, already it is in motion. As already it is in motion, obviously it has some initial velocity. So this is what actually the situation which we are going to assume. Okay, fine. Look at here, children. So here is an object. So we are starting, means we start observing the motion of an object, so that we have taken the time 0. So at a time is equal to 0, children, the body has some initial velocity, let us say u. So here u is the initial velocity and it is moving with uniform acceleration a. So the body has some initial velocity u and it is moving with a uniform acceleration a. Then after time t, do you expect that it has same velocity? No, because there is an acceleration. Velocity is changing in a uniform manner. That's what. After time t, its final velocity will be v. Children, this is the initial velocity. This is the initial velocity, and here is the final velocity. So that in this time interval, the body has covered some displacement s. Clear? So here u is this initial velocity, v is the final velocity. In a time t, as it is moving with a uniform acceleration, it covers some displacement s. Okay. Now, so this is situation, children. So in this situation, again I'm telling you, in this situation, a is what here? Uniform acceleration. So now let us derive a first equation of motion. Children, let us recall once again. What is at any time, how can we, at any instant, how can you define the acceleration, children? Yes, so here acceleration is defined as dv by dt. Acceleration is defined as dv by dt. So get this, children. So it is actually here acceleration is a vector quantity, velocity vector quantity. Okay, as it is a one-dimensional motion, so we will be mainly talking about the magnitude. Why? As it is a one-dimensional motion, there is no change in the direction of motion. So as there is no change in directional motion, there is no point in talking about the direction. Okay, fine. So this can be written as, actually simply we can write here A is equal to dv by dt. Just we are taking its magnitude. Now get this dt this side, so that it can be written as dv is equal to A into dt. A into dt. So let us integrate on both sides. Integrate. So we know that from where to where the journey has happened here. So children, when time is 0, try to understand, when time is 0, the body has initial velocity u. When time is t, the body has final velocity v. Children, differentiation of dv, just let us recall, differentiation of dx can be written as x. So similar to that, integration of dv, sorry, not differentiation, it's integration. So this can be v. But here there are some limits, right? So this is lower limit u, upper limit v is equal to. So integration of a dt. Children, here a is a constant. Constant can't be integrated. So that's you have to take out of the integration. So integration a into. So then integration of dt will be t only, right? So it is a t. And here limits 0 to t. Now apply these limits. First substitute the upper limit, that is v, minus, then you substitute lower limit u is equal to a into upper limit t minus lower limits 0. So this will be v minus u is equal to at. So this can be written as v is equal to u plus at. U plus at. In fact, actually it should be written like this, children. V is equal to u plus at. So this is a scalar form actually, and the second one is a vector form. So children, v is equal to u plus at is a first equation of motion. Then what is the purpose of this actually? Children, here look at here. If an object has some initial velocity u moving with a uniform acceleration, then after time t, what will be its final velocity? So for that, we use this special equation, v is equal to u plus at. So to calculate the velocity of an object after time t, if it is moving with a uniform acceleration, then final velocity is given by this first equation of motion is equal to v is equal to u plus at. Okay children, just copy this so that we derive now second equation of motion. Okay, pause the video, copy it. Since it's very simple, don't make it complicated. Okay, now copy it, fine. Now let us derive a second equation of motion. We are going to derive a second equation of motion. Children, what is a velocity at any instant? At any instant, if an object is in motion at any particular instant, how can you define velocity, children? The rate of change of displacement is called velocity. Children, I am talking about at any instant only, right? So at a given instant, so velocity is defined as ds by dt. ds by dt. So as we are talking about the only magnitude today, so v is equal to, it can be written as ds by dt. Now this can be written as ds is equal to, children, get this dt this side, so it will be v into dt. V into dt. Now children, what is v actually here? V is the final velocity. And just let us recall the first equation of motion. So we know that v is equal to u plus at. So now our idea is that let us substitute this in the place of v. So now it can be written as ds is equal to u plus at into dt. Now let us simplify this. ds is equal to, multiply with this dt. So these two terms should be multiplied with the dt. Bring this dt inside. So it can be u into dt plus at into dt. at into dt. Now let us integrate on both sides. Let us integrate. Fine children. Now let us bring the integration for each and every term. So this can be written as integration of ds is equal to, so children, in terms of t, so u is a constant, right? In terms of t I am talking. So this can be integration of dt plus, here a is a what? Uniform acceleration, constant. Constant can't be integrated. So let us bring that constant out of the integration. then it can be a into integration of t into dt, integration of t into dt. So now children, this integration of ds can be as acha, limits. When a time is 0 children, when a time is 0, displacement 0. After time t, so the displacement is s. Now integration of ds can be s, and let us apply the limits 0s, and this will be u into integration of dt will be t. So limits 0 t plus children integration of t dt. So integration of x dx will be x square by 2, and obviously integration of t dt will be t square by 2. So a into t square by 2 limits 0 to t. So now you apply the limits. So upper limit minus lower limit. Anyhow, it is s minus 0 will be s only. So s is equal to u into t minus 0 will be t only. So it is u t plus. So here also t square minus 0 square. It can be t square only, right? So it can be written as a t square by 2. A t square by 2 can be written as half a t square. Half a t square. So children, this is the displacement travelled. This is the displacement travel, which gives a relation between displacement, initial velocity, time and uniform acceleration. Here nowhere final velocity is involved. So this actually scalar form of the second equation of motion. So in a vector form here, s is equal to u t plus half a t square. So when we can use this formula, already body has some initial velocity and moving with some uniform acceleration a. Then what is the displacement covered after time t? So in that case, we can use s is equal to ut plus half a t square. Especially displacement covered in a time t. Very important. Displace means body is moving after 10 seconds, not at a 10th second children. Difference is there. That we'll discuss later. So here this is equation of motion which is used to find the displacement travelled after time t. Is it clear? Just copy it. So this is the second equation of motion. Fine. Clear? Okay. So now we discuss the third equation of motion. Children, first equation of motion mainly we use, of course, any three out of the three physical quantities. If two are given, of course, you also can use that, but especially final velocity. And the second equation of motion mainly displacement covered after time t. Now third children, and here children, what is the acceleration? What is the acceleration? Rate of change of velocity. What is the displacement here? Sorry, what is the velocity? The rate of change of displacement is called what? Actual velocity, right? Yes, look at here. So I am writing just magnitudes I am writing. So v is equal to ds by dt. Children, here let us multiply with a dv and divide with a dv. Anyhow, this will get cancelled. It will be 1 only. So nothing makes different, right? Okay. So this can be written as ds by dv and a dv by dt. Can we write? Yes, we can write dv by dt into ds by dv. Now look at children. So v is equal to, we got children, dv by dt. It is nothing but rate of change of velocity is called what? Acceleration. Okay. So a into ds by dv. Now get this dv this side children. So it can be v into dv is equal to a into ds. Now let us integrate on both sides. Let us integrate. Children, when a velocity, initial velocity is u, the displacement is 0. Okay. And after velocity v, the displacement covered is s. Children, integration of v dv is what? Integration of x dx is x square by 2. Similarly, this can be written as v square by 2, but don't forget the limits. So lower limit is u, upper limit is v is equal to. And then a is a constant, can't be integrated. So you can bring outside. So integration of ds will be s only. So a into s. So here limits 0 to s. Now apply the limits children. So this can be written as v square minus u square by 2 is equal to a into s. Now get this to this side. So it can be v square minus u square is equal to 2as. So this is a third equation of motion which gives the relation where time is not involved. It's a beauty equation. It's a beautiful equation, you know. Here in this is a equation of motion where time is not involved. If you can the first two equation of motion, v is equal to u plus at, s is equal to ut plus half at square. But in third equation of motion, time is not involved. So this is a scalar form, children. Scalar form. But how can we write in vector form? You know, this is v dot v plus, sorry, minus, how minus will become plus, okay, minus, and u dot u is equal to 2a and s. So this is the third equation of motion. So first one is v is equal to u plus at. Let us write here. First equation of motion we got v is equal to u plus at, and the second equation of motion s is equal to ut plus half at square, and the third equation of motion is v square minus u square is equal to 2as. So the special equation of motion is there, that is s nth. The displacement travelled in a nth second is equal to u plus a by 2 into 2n minus 1. Of course, this in today's class we are not going to derive. Yes, in a very next class we will see how to derive this, because of course as it is a bit special one, so many numericals can be expected. So about this especially the derivation and some numerical part, okay, we'll try to discuss in next session. Okay, so in this session only 3 equations of motion. Children, here how to calculate, you know, average velocity. Then in this case, children, how to calculate the average velocity? Children, here as the body is moving with a uniform acceleration, when a body is moving with a uniform acceleration, in that case average velocity can be written as displacement by time, but here look at here, this displacement equation, just you substitute here, then what do you get here? Ut plus half at square by t. So this can be written as ut by t plus half at square by t. T square, t gets cancelled. Okay, so here we need a space. Can I erase this? Okay, I'll erase this. So this can be, look at children, so this can be written as average velocity is equal to u plus half at. But half at is what, children? So we know that acceleration is equal to change in velocity by time. So then can we write change in velocity is equal to at? Yes, can substitute here. So this can be u plus v minus u by t. Let us take a LCM, 2 into, sorry, by 2 it will get, so 2 times it will be 2u plus v minus u. So here 2u minus u, it will become plus u, right? So this will be u plus v by 2. So this equation, this formula is used only when a body is moving with a uniform acceleration. Then only we can say the sum of the initial and final velocity by 2. Okay. Children, we know that here displacement is equal to velocity into t. Actually this velocity is what? Actually average velocity. In that place you can substitute this. Then s is equal to v plus u by 2 into t. Don't get confused here. What is this v? This is the final velocity, children. This is what actually average velocity. So especially these two formulas are used only when a body is moving with a uniform acceleration. Okay, children, fine. So this is today's session. In the next session, we'll just discuss the derivation of the displacement covered in a nth time. Okay, children. Thank you so much. All the very best.